everyone. So in preparation to your upcoming test, I'll go over some questions from your practice test. Okay, let's begin by doing this question here. Limit of f of x as x approaches 8 from the left is equal to 2, and the limit of f of x as x approaches 8 from the right is also equal to 2. But f of 8 does not exist. What can you say about the limit of f of x as x approaches 8? Now, by definition, to say that the limit exists as x approaches a, this one exists if and only if the left-hand limit of f of x as x approaches a from the left is equal to the right-hand limit of f of x as x approaches a from the right. So we only need to satisfy this for us to be able to say that the limit exists, even if the function is not defined at that particular value or at x equals a. So in this case, since the left-hand limit and the right-hand limit are equal, then we say that the limit of this function as x approaches a exists. All right, so it exists. And if it exists, what is the value? Where does the limit approaching to? It approaches to this number here. So it is approaching to 2. Check your answer. Very good. Now, consider the graph of the following limits. So we are given here the graph of a function, and we are to find the limit of the function as x approaches -1. Now, to examine limit, you look at the x value, -1, and then you trace your function. Where is your function approaching to? Where is the function approaching to as your x goes closer to that value? So we say x equals -1, right? So this is x equals -1. This is -1. Now, as x approaches -1 from the right and from the left, your function, you could trace your function from the right of, or from the right of -1, and it is approaching to this point here. Similarly, from the left of -1, if you trace your function, it is approaching to this point here. So even if it's not defined at that point, as long as it is approaching to that same point, we say that the limit exists. And what is the value? It is that y value here, which is negative. Where's the x coordinate? Oh, this is the x coordinate. So that is y equals 1. Okay, so this is the x coordinate. So that means that the limit here of f of x as x approaches -1 is 1. What about the limit of the function as x approaches 1, +1? This is +1. Notice that from the right of +1, it is approaching to the point here, that is x equals 2. But from the left of 1, as x approaches 1, from the left of 1, your curve is approaching to a different point. It is approaching to 4. So because the left-hand limit and the right-hand limit are not the same, we say that the limit of f of x as x approaches 1 does not exist. Next question. Explain why limit of f of x as x approaches 2 in figure A exists, but the limit of f of x as x approaches -2 in figure B does not exist. Okay, so let's explain this. Now, I copied this here. So the limit here on this first figure exists because the left-hand limit, if you look at this function here, that is x equals 2. The left-hand limit, so notice that the function is approaching to that point, so that means the limit of the function as x approaches 2 from the left is equal to this value here. That value is 2. So that is equal to 2. And also, if you take the limit of that same function, f of x, as x approaches 2 from the right. So now let's look at the right side of 2. This is the right side of 2. The curve at the right side of 2 will actually go, is as you go close to x here, it will go close to the point here, which is also 2. So that means because the left-hand limit is equal to the right-hand limit, then the limit exists. But for this second figure here, the left-hand limit of small f of x as x approaches -2, as x approaches -2 from the left. So if you look at from the left side, it is approaching at this point here. So the curve goes close to the point here, and that is -1. But if you take the limit of the function as it approaches -2 from the right, it is approaching to a different value, and that is -0.5. Now, also because you see a jump here, like you see a break on the graph. So if you see something like that and like that, then because of this break here, the limit of that function does not exist. But if there's just a hole, then the limit of that function at that point exists. And in other words, if you stick to the definition, because the left-hand limit is not equal to the right-hand limit, then the limit does not exist. Okay, so when you input the answer here, the limit of the function, they're equal. The left-hand limit is equal to the right-hand limit. And what is the limit? We know the limit exists because the left-hand limit is equal to the right-hand limit. And for the second one, the left-hand limit is not the same as the right-hand limit. So they're not equal. And so therefore the limit does not exist. Okay, so let's proceed to the next question. Here you are to construct the table and find the indicated limit. So if you are to do this, I will not do this type of problem, but if you are to do this, all you need to do is look at the values here, the different values here, the x values, and plug it into that function. Okay, so you just have to choose 2.9, replace x here by 2.9, and then the denominator also 2.9. Plug that into your calculator. And whatever you get, you have to input it here. Make sure to type integers if you get a whole number or decimals, but round it off to 4 decimal places as needed. Again, these are the x values that you would use to input to the function here to get the corresponding y values. All right, so now here you are given that the limit of f of x as x approaches 2 is 3, and the limit of g of x as x approaches 2 is 15. Use the limit rules to find the limit below. So we are looking for the limit of f of x over g of x. And so now to compute this limit here, so the limit of f of x over g of x as x approaches 2 is equal to the limit of f of x as x approaches 2 divided by the limit of g of x as x approaches 2. That's properties of limit. And then, since we're given the limit of f of x as x approaches 2 to be 3, so we have 3 over the value here. That's given to be 15. And so this is equal to 1 over 5. So the limit of f of x over g of x as x approaches 2 is 1/5. Now, similarly here, let's use the properties of limit to evaluate the given limit. So since we have limit of f of x minus g of x, that means that you can distribute the limit over subtraction. So therefore, this is just equal to, that is just equal to the limit of f of x as x approaches 7 minus the limit of g of x as x approaches 7. Now, the limit of this is just equal to 9. This here is equal to -6. So you have negative of -6. So that means this is equal to 15. So you have 9 plus, this becomes plus 6 is equal to 15. Right, so in this question, we are to use the properties of limits to help decide whether the limit exists. If the limit exists, find its value. Okay, so we are given x squared minus 1 over x plus 1, and we want to evaluate the limit of this rational expression as x approaches -1. So to solve this, we will have to use techniques that we learned in class. What you would do is you would factor the numerator. So notice that this numerator here is factorable. So why do you need that? Because if you actually plug this in, so if you plug this in, if you replace x by -1, you get 1 minus 1. So you get 0 over, and then the denominator is also 0. So if you get a 0 over 0, that's indeterminate. So in that case, if you have something like that, you would need to factor the expression that can be factored. And somehow there is a common factor that is both in the numerator and denominator that's making them both equal to 0. And you want to cancel that factor. So in this case, if you factor the numerator, you have x minus 1 times x plus 1. And the denominator is x plus 1. Now, notice that x plus 1 is a common factor. That is the factor that's making both numerator and denominator equal to 0. So we'll cancel that. We're able to reduce this expression into this. Then now we can evaluate the limit. So when you evaluate the limit, you just have to plug in, replace x by -1. So you have -1 minus 1. The answer is -2. So the limit here exists and it's equal to -2. Next number, we are given this expression and we are to evaluate the limit as x approaches 49. Notice that if you replace x here by 49, the square root of 49 is 7. So 7 minus 7 is 0. And likewise, if you plug in 49 in the denominator, you have 49 minus 49. So you have 0 over 0, and that is an indeterminate form. You cannot say that it does not exist. So another technique that we could also use is by rationalization, rationalizing method. So here, because it's indeterminate, we can use the rationalizing method, especially that this involves square root. So if you have something like that, you can multiply this by its conjugate. So you can multiply that by x plus 7. And then you do the same thing in the denominator. Now, you recall that if you multiply x minus a times x plus a, this is equal to x squared minus a squared. So here we have, you just copy limit first, and then you multiply the numerator. This times this, using the formula here, will just be equal to x, because the square root of x is just x, minus 49. 7 times 7 is 49. Divided by x minus 49 times square root of x plus 7. Now, x minus 49 will cancel. Then after that, you can now plug in. So let's plug in 49 in the denominator. You would get, so if you plug in 49 here, you have the square root of 49, that is 7. Okay. That is square root of 7, 49, and then square root of 49 is 7, plus 7 in the denominator. So you have 1 over 14 as the answer. Now in this next problem, we have 5x over 8x minus 9, and that is x approaches infinity. So this is under the topic of limits at infinity. Now we have a technique here that we could use. To compute for something like this, you can just compare the degrees in the numerator and in the denominator. I'll show you how to do that. So again, this would only work if the limit, if you're looking at the limits at infinity. So if it is x approaches either positive or negative infinity. So what you would do is you will multiply both numerator and denominator by 1 over x, in this case x raised to the degree, but the degree here is just 1. So you can multiply 1 over x in the numerator, and you also do the same thing in the denominator. So you will have limit x approaches 8 of, now if you multiply 1x times 5x, you actually get 5. And then each term in the denominator will be multiplied by 1x. So 8x times 1x is 8. And negative 9 times 1x is negative 9 over x. Then evaluate the limit. Now, remember, if you have a constant divided by a very large number, divided by infinity, that is just 0. So that means this term here goes to 0, because if you plug in infinity to x, you will have 9 minus 9 over infinity, and that means this goes to 0. So the answer here is 5 over 8. So the limit exists and the value is 5 over 8. Now I also have a shortcut. The shortcut is to just compare the degrees for numerator and denominator. So what you would do is you would just look at the leading terms. So 5x over 5/8, you divide that. 5x over 8x, then you divide it. The x cancels out. Then you just have that constant. That constant, the limit of a constant is also that constant. And that is the limit of that function. Now let's consider another problem. Here we are to find the limit of this expression as x approaches infinity. So this is again another limits at infinity problem. So as a shortcut, as I've mentioned, what you can do is you can compare the degree for numerator and denominator. If they have the same degree, the limit is just the ratio of the coefficients of the numerator and the denominator, coefficients of the leading term in the numerator and the leading term in the denominator. Or in other words, what you can do is you can just take the leading term, in the numerator and also take the leading term in the denominator. Okay, you take the leading term in the numerator and the leading term in the denominator, and then you divide that. So you get limit x approaches infinity of 2x squared over 2x squared. That is just equal to 1. So limit of 1 is also equal to 1. So the limit here is 1. It exists and it's equal to 1. So now another similar problem. So you do the same thing. You get the leading term in the numerator and the leading term in the denominator, and then divide and then take the limit. All right, so here, this is just the same as the limit as x approaches infinity of, again, leading term in the numerator, 9x cubed, leading term in the denominator, 6x to the fourth, divided. You cancel x cubed, and you only have x in the denominator. The 9 and the 6 cancel, so you have 3, 2. So this is equal to the limit as x approaches infinity of 3 over 2x. Now, if you replace the denominator by 2 times infinity, that is just infinity. Remember, constant over infinity is just equal to 0. So the limit here exists and it's equal to 0. Now for the next problem here, we are given a piecewise function and we are asked to evaluate the limit of the following functions as x approaches 3 and as x approaches 6. Okay, so let's look at the first one. When you say limit of the function as x approaches 3, notice that 3 is an endpoint of that interval. So when you take the limit, you will have to consider the limit from the left. So x approaches 3 from the left. And you also get the limit of the function as x approaches 3 from the right. Now, if you get the same value here, then that limit exists and it's equal to that number. If you get 2 different values, that means the limit does not exist. Now here, if you have, let's take a look at the first one. Limit of f of x as x approaches 3 from the left. From the left, that means less than 3. So if x is less than 3, the definition of f of x is equal to x minus 1. So you would replace the f of x here by x minus 1. Okay, again, because that is the definition of that piecewise function when x is less than 3. That means it's to the left of 3. So you have x minus 1 here. Then you evaluate the limit. You evaluate that by plugging in to the value of x here, the value of x that's given. So you replace x here by 3. So now you have 3 minus 1, and that's equal to 2. The second one here, x from, if you have limit as x approaches 3 from the right, that means x is greater than 3. When x is greater than 3, according to the definition here, your f of x is just 2. So this is limit of 2 as x approaches 3 from the right. So limit of a constant is just equal to that constant. Now we see that the left-hand limit is equal to the right-hand limit. They're both equal to 2. So therefore, we can conclude that the limit of our function as x approaches 3 is equal to 2. Okay, so that's letter A. Now for letter B, we want to find we want to evaluate the limit of the function as x approaches 6. And again, 6 is an endpoint of that interval, the endpoints of intervals. So therefore, we have to look at the limit, the left-hand limit and the right-hand limit of the function as x approaches 6. So we have f of x as x approaches 6 from the left, and we also need to evaluate the limit of the function as x approaches 6 from the right. Now, according to definition, from the left, that means less than 6. If x is less than 6, f of x is equal to 2. So this is equal to 2. X approaches 6 from the left, so that is just 2. Now, if x is greater than 6, it is defined as x plus 2. So this is limit of x plus 2 as x approaches 2 from the right. Oh, no, not 2. 6 from the right. Then you plug in 6 into that equation. So you will have 6 plus 2, which is equal to 8. Now, you see here that the limit of the function as x approaches 6 from the left is not equal to the limit of the function as x approaches 6 from the right. Therefore, the limit does not exist. It does not exist. So let's go back to the problem here. This is the first one. What we got was 2, right? Oh, okay, hold on. I have to type in 2. That's what we got. Oops. And the number here, which is 2. There we go. That's for letter A. Okay, then we're given letter B. Now for letter B, we would say that the limit is not negative infinity nor infinity, and it does not exist. So when would you say does not exist? If the left-hand limit is not equal to the right-hand limit. And you pick either positive or negative infinity otherwise, okay, when it's appropriate, okay? So the answer here is B. Now let's consider the next problem here. Find the value x equal to a where the function is discontinuous. Now for the point of discontinuity, give a, f of a if it exists, and the limit of the function as x approaches a from the left and from the right, and also give the limit of the function as x approaches a. Identify which conditions for continuity are not met. So when you say a function is continuous, if you are given a graph, that means that you could trace your graph without lifting your pen. So here, you would have to lift your pen because there's a hole here. And then you would jump there, go back again, and then continue to trace your curve. So that means that by just looking at the graph here by inspection, we know that this is that the function is discontinuous at this point here. And what is that point? Okay, so this point is x equals 1. So it's discontinuous at x equals 1. So so x equals 1. Okay, so I copy the function here. So we want to find the value for x equals a. So what is that a? X equals a. So a is, in this case, discontinuous at this point here, and that is 1. X equals 1. A equals 1. Now, does f of a exist? So what is f of 1? What is f of 1? F of 1 is equal to that point here, right? So, and that exists, and it's equal to, let's count, 1, 2, 3, okay, hold on, 1, 2, 3, 4, 5. So it is equal to 5. F of 1 is 5. Now find the limit of the function f of x, so the function f of x as x approaches 1 from the left, and also the limit of the function as x approaches 1 from the right. So from the left, you're just going to trace it from the left side of 1 is this side here. So as you approach you trace your function is approaching to this point here as x approaches 1 from the left. And what is that value? That is 1, 2, that's negative 2. And similarly, if you approach your point, if you trace your curve when x is approaching 1 from the right, it would still approach at this point here, that point, and the corresponding y value of that point is -2. Now, we have seen here that the left-hand limit is equal to the right-hand limit. So that means that the limit of the function exists. The limit of the function as x approaches 1 exists, and it's equal to 2. Now, is the limit exists, but the function is discontinuous. What condition was not met for continuity? Now, we have 3 conditions that needs to be met. The first condition is that the function needs to be defined, so that's correct. Here, the limit should exist, that's also good. The third condition, and that was not satisfied, is that the limit of the function as x approaches a must be equal to the value of the function at x equals a. These two are not equal. So see, the limit of f of x as x approaches 1 is not equal to f of 1, right? Because this is 2 and that is not equal to 5. So that third condition was not met. Therefore, the function is discontinuous at x equals a. Now let's consider the following problem. Here, we are given a function and we are asked to find all values for which this function is discontinuous. Now, if you are given a rational function, the possible points of discontinuity are the zeros of the denominator. Points of discontinuity are the zeros of the denominator. So in other words, you just have to get that denominator and then find the zeros. So this means you have either x equals 0 or x minus 7 is 0, and that is x equals 7. So these two values of x are just possible points of discontinuity. We still need to double check if that function is discontinuous or not at those points. Now, to do this, you can either use limits, or you could also use the techniques that you've learned in algebra. And what are those? Like, the easiest is to do an algebraic technique, algebraic manipulation. So what you would do is you would plug in these values of x here in the denominator, in the numerator, sorry. You plug it in the numerator. So if you get a 0 also in the numerator, then that means that you have a hole at that point. You have a hole at that point because, you could cancel that common factor and then you would be able to find the limit. The limit exists at that point if the numerator is also 0. But if when you plug it into the numerator and you get a constant, so that means that the limit does not exist. So you have an asymptote at those points. Okay, so let's go ahead and plug that in. So let's have f at 0. What do you get? 6 over 0 times -7. So that means that at x equals 0, we have an asymptote. We have a vertical asymptote. And then if you plug in also similarly, if you do 7, if you have f at 7, you would get 13 over 7 times 0. So that means, so you would still have a 0 in the denominator, 13 over 0. That gives you infinity, right? So that means that at x equals 7, we have a vertical asymptote. Now, if needed, you would have to evaluate the limit. Let's take a look at the choices here. Did it ask you to evaluate for the limit? So it says here the function is discontinuous at single value. Okay, so here at 2 values. So it is discontinuous at 2 values. The limit for the smaller value now, in this case, you would have to evaluate for the limit. Now the limit would either be positive or negative infinity. So in that case, we would have to use calculus to evaluate the limit here. Okay, so we know we have vertical asymptotes. All right, so this is your algebraic method, and you would not know if it's positive or negative infinity in that case. Okay, so let's evaluate the limit of your function as x approaches the limit of 6 plus x as times x minus 7 as x approaches 0 is equal to, okay, so this one is, we have to get the limit from the left and limit from the right. Because you could also have, you can have discontinuity at those points, but the limit does not exist. Like, for instance, if the graph would look like this, for instance, at x equals 0, if the graph looks like that, it goes up to infinity here and also goes up to infinity. In that case, they're approaching at different values. So the limit does not exist. Although they're both, one is approaching at positive infinity, the other one is approaching at negative infinity. So we say that the limit does not exist at that point. But if you have something like this and they both, for instance, approach to negative infinity, like in that case, then we say that the limit approaches to negative infinity. And it exists, and it's approached to negative infinity. So this one, the limit of that function is negative infinity. Here, negative infinity. Then if the graph looks like that, okay, the limit of that function there, x approaches, in that case, 0, is positive infinity. So it exists, and it's equal to positive infinity. But if it looks like this, the limit of the function as x approaches 0 does not exist, because they both approach to 2 different values. I mean, they approach to 2 different values or expressions. So one is approaching to positive infinity, the other one is approaching to negative infinity. So now to properly compute it, so we have this, so we have 6, you plug in, so take the left hand limit and the right hand limit. So you have 6 in the numerator. In the denominator, that will just be 0 minus. Now, here you have also negative 7. So you have negative, negative. So this, when I say 0 minus, that means that the values as it approaches to 0 are coming from the left-hand side of 0. So those are the negative numbers. So those negative numbers times a negative number, that means a 0 plus. So this means this is equal to positive infinity. Now, let's take a look at the right-hand limit. So limit as x approaches 0 from the right of 6 plus x over x minus 7. The numerator will just be 6. If you plug in to this one, you will have 6 plus 0. 0 plus is still positive 6. And then here, the denominator will be 0 plus. Now, 0 minus 7, that's negative 7. So negative. So here, when I say 0 plus, again, the values as it approaches to 0 are positive, coming from the right side of 0. So those are positive values, times negative is negative. So that becomes a 0 minus, or So that means you have 6 over 0 minus is negative infinity. It follows the rule of signs. Positive over negative is negative. So because we got a positive infinity and a negative infinity here, then we say limit does not exist. So that is for x equals 0. Now let's consider x equals 7. So let's take a look at the limit of that function, 6 plus x, as x approaches 7 from the left. You have x minus 7. And then also evaluate the function as x approaches 7 from the right. 6 plus x over x times x minus 7. Now you plug in values. So numerator, 6 plus 7 is 13. And then 7 times, now we have 7 minus, so that means left-hand side of 7. What are the values at the left-hand side of 7? Like 6.9. So if you have 6.9 minus 7, so it's a number less than 7 minus 7, you have 0 minus. Okay, so the answer is close to 0, but it's coming from a negative value. So that means 13 over 0 minus is negative infinity. Similarly, you do the same thing. You plug into the numerator. You have 13. Denominator is 7. Now, the 0 here, we look at the sign for that 0. If you have 7 plus, so that means coming from the positive side, or the right-hand side of 7. So maybe 7.1. So say, for instance, 7.1 minus 7. It is very close to 0, but it's on the positive side. So that means this is 0 plus. So now 13 over 0 plus means positive infinity. So now again, because we got two different signs here, we have negative infinity and positive infinity here. Those two are not equal. So that means we say that the limit of the function as x approaches 7 does not exist. So they're discontinuous at those points, and the limit does not exist. So if you go back to the choices here, the correct choice will be this one. The function is discontinuous at two values of x. Then you list down those two values of x. And the limit for both values does not exist and are not positive or negative infinity. Now, for this next problem, we are to determine the interval for which the function is continuous. If you are given something like this, all you need to do is remember the domain of the function. A function is continuous over its domain. So to get that interval, all you need to do is find the domain of this function here. Now, to find the domain of that function, because this is a square root function, you just need to make sure that the radicand, the expression inside that square root, 2x minus 3, should be greater than 0. So it should be positive. And then you solve for this inequality here. So you have 2x greater than 3, divide both sides by 2, x is greater than 3 halves. And then if you write that on interval notation, that will be 3 halves. There should be equality because that's not in the denominator. So it should be including 3 halves. So 3 halves to positive infinity. That is in interval notation.